I stood there at the edge of a world, vast and mysterious, unknown to most, a world of dreams for some and nightmares for others. A world in perpetual expansion, often said to be eternal and unchanging, filled with rules and freedoms, with shapes as easy to imagine as they are sometimes impossible to picture. For centuries, the greatest scholars have wondered if this world exists everywhere, all the time in the universe, if it is the language in which the world is written, underlying the whole, the one in which nature speaks, or if it exists only in our minds, in purely imaginary realms. It is there, apparently, in the Mathworld, that a dragon called Truth hides and lives. For some, truth, solid and eternal, could only exist here and nowhere else, only in this imaginary world. I'll give you a few seconds to ponder this idea. In history, many of those who set out to hunt these dragons, often as perfect as they are abstract, were drawn into the mathematical territories in which they had to venture in order to try to find them. Territories divided into regions, into counties, whose parts, however strange they may be, are held together by a single imaginary substance, from which no atom of the real world can escape, an immaterial substance called logic, the binder of fundamental building blocks that no acid can dissolve, that no black hole can reach. In the universe we live in, objects exist, and through language, we try to define them in order to think about them, to give them a name so we can talk about them. That is an apple. But it's also a shape, a color, a flavor, ingredients, and dozens, hundreds of other aspects of reality as well. But in the math world, the first fundamental objects, 1, plus, minus, the point, must first be defined in order for them to exist. These objects are nothing more than their definition, nothing less. And yet by creating these first entities, we make them appear in our minds, bringing them out of nothingness. And strangely enough, it's with these objects that a universe appears, with its rules and remarkable properties, and from then on, vast territories that are just waiting to be explored emerge in the math world. If two people imagine, in different languages and places in the world, and 1,000 years apart, the idea of one and addition, they will have brought into existence, in the same movement of their thought, the set of positive whole numbers. And by exploring this part of the math world, which contains arithmetic, they will be able to discover the same calculation rules, come across the same results, the same surprising numbers, the same harmonies, the same paradoxes. And all this with only the idea of one and addition. And mathematicians have defined quite a lot of concepts. Some say that it's in this world of variety, thought to be infinite, capable of changing form without changing substance, of redefining itself while remaining coherent, that the secrets of the universe, crowbars for Pandora's box, are kept. It is there, in the labyrinth of their minds, that so many motionless knights have gone on heroic quests, which can only be told in languages that seem almost Kabbalistic. But most often, mathematical truths can stand right there in front of you and completely elude you. We can show them to you, explain them to you in 1,000 ways, through 1,000 detours, make you circle around them, point them out to you, right there, just there. It's obvious, can't you see? Invisible, incomprehensible, absent. For many people, myself included, math often refuses to be understood. Don't doubt yourself. Be patient, try to visualize, take your time, let it come, do something else, and come back to it, until the breakthrough happens, if it does, that sudden click. That moment when a proof becomes obvious, when it appears in its entirety, shouting at you, Eureka! Only then, a small piece of the math world belongs to you, trust me, and let's take a little journey inside this math world, starting with the forest of ancient numbers, the integers. Personally, they appear to me as branching trees, but in reality, they are nothing but pure quantity. Among them, the integers, there are all imaginable sizes of numbers, and even those that are not. The ones that stand out first here are the integers I already told you about, the ones made up of sums of 1. From these numbers, the ancient Greeks built temples, religions, and sects. They are so simple that they come to us almost instinctively, everywhere, all the time. All you have to do is count, just look. How many steps does this staircase have? How many grains of sand are on this beach? How many grains of wheat to get through the winter? How many stars in the July sky? The answers to these questions are all sums of 1. But forget for a moment with me what you're trying to count. Because the truths we discover while exploring the world of these numbers apply to stars, grains of sand or wheat, or any other whole number. Let's take a concrete example and start contemplating together the bewildering immensity of this abstract world. In the forest of all positive whole numbers, which we call n for natural, some can be divided, split into equal parts, while still remaining whole numbers. 12 is 3x4, or 4x3, or 2x6, or 12x1. These divisible numbers are the vast majority of whole numbers. Now look, let me show you a random oddity. Among whole numbers, some like 628 or 33,550,336 are divisible. You perfect. Because they are equal to the sum of all their divisors. 6 is divisible by 1 by 2 and by 3 1 plus 2 plus 3 equals 6. You got it. Perfect. 28 is divisible by 1 like all numbers, by 2 like all even numbers, by 4 by 7 and by 14. 1 plus 2 plus 4 plus 7 plus 14 equals 28. I'll let you try with 33,550,336. There are currently 51 known perfect numbers. All positive and all ending with 8 or 6. This one is perfect. Those are perfect too. The largest perfect number discovered so far has 12,140,858 digits. That's the one. 2 to the power of 20,996,010. This number is about 150,000 times larger than the estimated number of atoms in the observable universe. In this single forest of whole numbers, there's a lifetime of possible discoveries. The study of this part of the math world is now called number theory. Many of those who ventured there had fun searching for some prime numbers. Numbers that are only divisible by one in themselves, kinds of monoliths, impossible to split into equal whole parts. These prime numbers seem to be distributed randomly. In any case, no one has ever found a pattern to find them. Since antiquity, however, it has been proven that there are infinitely many of them, and we also know that they become rarer and rarer as we go higher and higher. The discovery of megaprime numbers, numbers made up of more than 1 million digits, is now a quest for mathematicians armed with their white chalk, their blackboards, and their supercomputers. The latest one to have been found at the time I'm writing this video is 2 to the power of 82,589,933 minus 1. Don't go away, stay with me, you'll see, it's fascinating. Let's imagine that one day, a super powerful program or a genius mathematician manages to find a way, an equation that allows us to uncover all the prime numbers. We could then number them in order to count them. P1 for the first prime number, P2 for the second, and so on, all the way to infinity. Because remember, there are infinitely many of them. Each prime number would be associated with an integer, and each integer with a prime number. And then, we would realize that there are as many prime numbers as there are natural numbers. Your brain tells you infinity seems to be a logical problem, a shadow among many others. And in this world of obviousness, suddenly, at high speed, a 404 error appears, a bug in the matrix, letting you know that there is right here a problem, an abyss. A paradox capable of hitting our perceptions with the delicacy of a cast iron door. How can a set have the same number of elements as one of its subsets? Okay, let's go over this again. 1 plus 1 equals 2. Okay, 2 plus 2 equals 4. Okay. So 1 plus 1 plus 1 plus 1 plus 1 up to infinity equals half of 2 plus 2 plus 2 plus 2 up to infinity, right? You got lost. What you're imagining are sequences, not sets. These two sequences go to the same place. They go to infinity. And if you're wondering, yes, there are as many even numbers as there are integers. What I mean by that is surveying the math world. Poorly equipped to wander through these mathematical lands, you risk getting a nosebleed. Let's stop looking up at the peaks of infinity and set our sights on the ground. 0, the void. And behind on the other side, dive toward the negative numbers, kinds of hollows, holes, quantifiable absences. A mirror world of positive integers. And in this below, just like above, infinity is there too, welcoming and just as ready to make you lose your mind. Fleeing between two quantities, destroying the integers, and turning them against each other, dividing to better rule. And once again, encountering infinity. All of this because of a few ideas. The one, the plus, the minus, the sharing of what you get. Now, to clear our minds and give these ideas some shape, let's leave the forest of numbers and enter the plane of geometry. Here, the plan is to create in your mind the basic entities that inhabit this part of the math world. Now, everything begins not with the one, but with the idea of the point. An extremely powerful conceptual object that seems obvious, even though it actually exists nowhere else but here, in the math world. Because the point is just an infinitely precise position. It has no height, no length, no width, no area, no surface. It's not a sphere. The smallest element in the physical world, atom or particle, is infinitely larger than it. We agree, in the real world, the point doesn't exist. But thanks to the knowledge drawn from the plane of geometry, which comes from the invention of the point and all the ways to connect them together. In the real world, human beings have been able to think about shapes, trajectories, build cathedrals, and land on the moon. If there's only one point, you live alone in dimension 0. If there are 2 points, you can connect them and catapult yourself into dimension 1 by creating a segment. And if, on either side, you extend this segment endlessly without ever stopping, then once again you're dealing with infinity. And now, let me give you something to think about. Yet another little idea to chew on, at least if it hasn't already clicked in your brain. First of all, it's actually quite easy to show that there are as many points in a segment as there are on a line. I'll let you think about that. You can also show that there are more points in any segment than there are whole numbers. If you want to think about it, grow the forest of numbers on your line by placing a 0 and a 1 on it. Take a deep breath. So, you can show that there are too many points between 0 and 1 to be able to count them. You can even show that there are too many points in any segment, no matter how small, to be able to count them. And that's true even if you know how to count to infinity. In other words, there are more points between 0 and 1 than it is possible to count. So there are more points in a line segment than there are whole numbers, and so there are infinities that are bigger than others. The 1, the plus, the minus, the point, n-dimensional spaces, perfect spheres, vectors, matrices, sinusoids. All these imaginary objects have an independent existence in the math world. Every day, mathematicians discover, clear, and build ever more abstract, ever more exotic territories made of imaginary materials. And every day, physicists, chemists, acousticians, biologists, architects, computer scientists, engineers use these imaginary diamonds, mined from blackboards at the heart of the math world, to explain an absolutely astonishing variety of phenomena. But then why, or rather how, does this abstract world fit so well with reality? What kind of relationship exists between the math world and our own world? Are they two sides of the same coin? Or is it just a happy coincidence that it works, that one allows us to decipher the other? Is mathematics a form of discrete writing in which the language of nature is encoded? I'm going to take a deep breath and wait for that click moment.